Nature loves symmetry. From the delicate petals of a flower to the perfect structure of a snowflake, symmetry seems to be a fundamental feature of the world around us. But sometimes, nature chooses to break this symmetry in a way that leads to deep and fascinating consequences. This is the essence of spontaneous symmetry breaking, SSB, a concept that underlies everything from phase transitions in materials to the fundamental forces of the universe. But what does it mean for symmetry to break spontaneously? And why is this concept so crucial to understanding physics at its deepest levels? Let's explore this intriguing idea step by step. In physics, symmetry refers to transformations that leave a system unchanged. For example, a perfect sphere looks the same from any angle. This is rotational symmetry. If you swap the left and right sides of an equilateral triangle, it remains unchanged. This is reflectional symmetry. However, symmetry does not always stay intact. In certain conditions, a system can begin in a symmetric state but then choose one specific configuration, breaking the symmetry in the process. The system itself could have remained symmetrical, but instead, it picks a particular direction or state. Imagine balancing a sharpened pencil perfectly on its tip. In this position, the system has complete rotational symmetry. It looks the same from all sides. However, this balance is precarious. The slightest disturbance will cause the pencil to fall in one particular direction. The laws of physics governing the pencil remain symmetric, but the outcome is not. The symmetry is broken spontaneously. This is the core idea behind spontaneous symmetry breaking. The fundamental rules remain symmetric, but the actual state of the system does not. Now that we have a simple analogy, let's explore how this idea appears in fundamental physics. 1. The Higgs mechanism, giving mass to particles. Perhaps the most famous example of spontaneous symmetry breaking is the Higgs mechanism, which explains how elementary particles acquire mass. In the early universe, all particles were massless due to a highly symmetric state. However, as the universe cooled, a field known as the Higgs field settled into a non-zero value everywhere in space. This choice of a particular vacuum state broke the underlying symmetry of the fundamental forces, and as a result, some particles gained mass while others remained massless. This process explains why the weak force, responsible for radioactive decay, behaves differently from electromagnetism, even though they were once part of the same force. The Higgs boson, discovered in 2012 at the Large Hadron Collider, LHC, is the quantum signature of this symmetry breaking process. Its discovery confirmed one of the most important predictions of modern physics. 2. Magnetism and the Curie temperature. A more tangible example of spontaneous symmetry breaking happens in ferromagnetism, the phenomenon that gives magnets their ability to attract or repel objects. At high temperatures, iron atoms are in a state of disordered chaos, where their tiny magnetic orientations, spins, point in all directions, preserving symmetry. But when the material cools below a critical temperature, called the Curie temperature, the atoms spontaneously align in one direction, forming a magnet. This breaks the rotational symmetry that existed at higher temperatures. Interestingly, the fundamental laws of magnetism remain the same. It's just that the system chose a specific state from many possibilities, breaking the symmetry in the process. 3. The Mexican hat potential, a visual representation. One of the best ways to visualize spontaneous symmetry breaking is through a concept known as the Mexican hat potential. Imagine a smooth, circular hill with a dip in the center. This shape resembles a Mexican hat. At the very top of the hat, the system has perfect symmetry. It looks the same in all directions. However, this is an unstable equilibrium. The slightest push will cause an object at the top to roll down the hill into one particular direction. The system can have fallen in any direction, all of which are equivalent initially, but once it settles, the symmetry is broken. This model is often used to explain how the Higgs field works. Before symmetry breaking, all directions are equivalent, the system is symmetric. But when the Higgs field takes on a specific value, a single direction is chosen, breaking the symmetry. Spontaneous symmetry breaking is not just a quirky phenomenon, it is a cornerstone of modern physics. It explains why fundamental particles have mass, via the Higgs mechanism. Why some forces in nature appear different even though they were once unified, such as the electroweak force splitting into electromagnetism and the weak nuclear force. Why superconductors work, where electrical resistance disappears due to a broken symmetry state in quantum fields. Why the early universe evolved the way it did, including the formation of galaxies and cosmic structures. One of the most fascinating aspects of spontaneous symmetry breaking is that the underlying laws remain symmetric, even though the observed outcome is not. This raises profound philosophical and scientific questions. Is symmetry truly broken, or is it just hidden? Some physicists believe that what we perceive as broken symmetry might just be an illusion, and a deeper underlying symmetry still governs reality. Can broken symmetries be restored? In extreme conditions, such as the high-energy environment of the early universe, symmetries can be restored, meaning that fundamental forces may have once been unified. Could there be more hidden symmetries yet to be discovered? Some theories, like string theory, suggest that even deeper symmetries exist, shaping the very fabric of space-time. Spontaneous symmetry breaking is one of the most profound ideas in physics. It governs everything from the mass of particles to the behavior of magnets, the structure of the universe, and possibly even the nature of reality itself. It tells us that symmetry is not always preserved, but paradoxically, breaking symmetry leads to new patterns, new structures, and deeper understanding. Just as the fall of a single pencil can break perfect symmetry and yet create a defined, structured world, so too does spontaneous symmetry breaking shape the universe in ways we are only beginning to comprehend. The next time you see a magnet, ponder the Higgs boson, or even knock over a pencil, remember, you are witnessing the power of spontaneous symmetry breaking in action. And that is the hidden order behind our seemingly chaotic world.